So in my last class, I discussed about linearized small signal state equations. Okay, for in generalized form. Okay, so here you are able to see the equations. I think all of you practice it in your home. Okay, and I think all of you are up to date about your class notes and you are preparing your final fair copies of the class notes. Okay, at the time of discussion I will ask for that class notes. Okay, so you have to submit it through online. So so day to day you have to update yourself. Okay, so I think you are able to understand that how would I get this generalized equation. So in this modeling means different types of modeling is available. Okay, so in literature means in references, so one by one I am going to be discussed. So now I have discussed the generalized structure, so we are implementing this method, okay, to our any of the converters. So for our example we are considering that non-ideal buck boost converter. Okay, so here you can see that buck boost converter you are considering, okay, with input current is Ig. Okay, you can say like that it is your inductor current. The rest of the parameters are same. If you followed my last class, so you can understand, I think so. So all of that parameters, so you know that state vectors. Okay, so state vectors are same it vt. Okay, these all are the state vector. So vg and vd all are that your input vectors. Okay, so I think you are able to understand. Then output vector is there, that is your yt, it is ig. Okay, means your input current. Okay, so it depends your output voltage, output parameters depends upon your input current. So model non-idealities means in ideal cases you are not considered those parameters. So when model are in non-ideal, so which parameters you are considered here? So first you are considering that RD on. Okay, so MOSFET on resistance. So first one is your MOSFET on resistance, RD on, and diode forward voltage drop, it is called that Vd. Okay, these two you have considered here. Okay, I think you are able to understand. It is your state variables matrix. Okay, so these two non-idealities you have considered. Okay, so now again that equation same thing. So sub interval 1. Okay, so when that switch is on you can say like that. So R on will be in your considerations, means MOSFET on resistance. So it is your equation, state equations are there. So we have written over here the state equations and current expressions. Okay, then you are expressed in the form of matrix. Okay, so that's your generalized equations. Okay, so you will get that value and it is your output equations. Okay, that is your state equations in generalized form. Okay, so from that expression you are able to find out a1, b1, then c1 and e1. Okay, all you are able to find out. Then in case of subinterval 2 you are able to get that values, that is your k. Again subinterval 2, that state equations. Okay, it means subinterval 2 means your MOSFET is off. Okay, if your MOSFET is off, so diode will be turned on, so you will get that forward voltage drop of the diode you have considered. So you can see that your equations consist of this parameter. Okay, so both of the equations you are able to see for the state equation and output equation. So here you are able to get that r1 is there. Okay, so here you are able to see that r1 is there. Okay, r1 is there. Okay, so I think you are able to understand that how to get that values. Okay, so now we can go for the generalized equation. So same methods are going to be applied. So your a equal to what? A equal to dA1 plus d dash a2. So simple thing, evaluate that average matrices. Okay, so you know that value of a1 value you are getting from here, it is your a1 value. Okay, then it is b1. Okay, a1 b1, then c1, and it is your e1. So you can replace them. Okay, so a2 value you are getting over here, it is a2 b2. Okay, then c2, and it is your e2. So now you can replace them in your expression. So you are replacing the value of a1, this is your a1 value. Okay, it is your a1 value. Then it is a2. it is your A2. Okay, this is A2 value, you can replace them and finally you will get that average value, so it is your A. Okay, in similar manner, you can able to get that value of B, okay, C and E. Okay, so all the parameter you are able to get it. So B equal to what? DB1 plus D dash B2. What is C? C equal to DC1 plus D dash C2. What is E equal to DE1 plus D dash D2. So you can replace them. So finally you will get that matrices. Okay, so all the values are there. Then you have to find out the steady state value. In steady state value, what you need to do, that value is constant. So di t dt. So that value should be constant. Okay, so if you are making it constant, so your input current making it constant, so that value, input side value will be 0. Okay, so that's why this 0 is coming. Okay, 0 equal to what? Ax plus bu. You know the value of a. Okay, so the value of a is coming from here. It is your a value. Okay, it is your a value. So you can put that value a. Okay, from here it is your a value. Okay, so put that value of a as well as b. Okay, a b, then c and e. Okay, both you can get it. So you replace them. Okay, you replace them, so you will get that final matrix. Okay, so what is your DC solution? So from here you have to calculate that value of I into V. Okay, so I and V calculations you have to I and V. So I means your inductor current in steady state, means DC current. Okay, inductor DC current, and capital V is your output voltage, means steady state, means final DC value. Okay, that you have to calculate it. Yeah, that you have to be calculated. Okay, so you will get that expressions from here. So all are in generalized mode. So if you know the parameters of that switching converter, so you can replace those values. Okay, and you can easily find out the value of I and V. Okay, that is your final motivation, final agenda. So you have to calculate the steady state value. So which are the state variables? So inductor current, capacitor voltage, and these two are the state variables. So that's why you are getting that steady state value of inductor current and capacitor voltage, means output voltage value. Here there is no ESR in capacitance. Okay, so you are only considering two non-idealities, that is your on-time resistance of MOSFET RD on, another one is forward voltage drop of that diode. Okay, so power diode. Okay, that's why DF. These two you have considered. So you will get that expression I and V in the form of RD on and VD. Okay, so that you have considered over here. So here you can see that it is calculated. So means you are able to get it that value. So R1 is there. Okay, here you can see that R1 is there. Similarly, you are getting that VD. Okay, so that you will also be getting over here. So both the equation you are getting that R1 is present, R1 and VD. Okay, like your steady state value of your state variables and IG. So both the cases you can see both that present in your equations. Okay, so that is your motivations and agenda. You have to find out it. Okay. So then you are getting the steady state equivalent circuit. Okay, so if you go for the steady state equivalent circuit, definitely, so it is your DC value. So both of the cases there is no isolation, both are similar. Okay, that values are connected, that's why it is connected in a single line. Okay, there is no isolation, but we are making it in equivalent, that's why you are considering one DC transformer, and that DC transformer having the turns ratio 1:D, and here you can see that in second side it is D dash to 1. So corresponding equivalent circuit for the DC transformer model. If I have some time, so definitely I discussed on portion based on that all the circuit, all the switching converter modeling in the form of DC transformer modeling. Okay, so especially we are using here in the form of means small variations of that values. Okay, of the DC values that we are only considering. So DC transformerized model is not discussed yet. Okay, so if I have some time, definitely I'll discuss on it. Okay, so first let me finish that portion. So after that controller, then if we get some time, so I'll go that for I can discuss about that portions. Okay, so here you can see that the DC state equations. Okay, so in DC state equations, so you can replace that value that previously you have obtained. Okay, so you can replace them, so it is 0 0. The state variables are 0. Definitely rate of change of state variable for the constant should be the 0. Okay, here you are getting that value of I, V, everything you are able to get it. So then you are getting that VG and VDF. Okay, so all are there. Okay, finally it is your input currents. Okay, input current in the form of state variables. Okay, so finally if you replace them, so you will get that equation. All of you please cross check that circuit diagram. Okay, if it is coming or not. If it is not coming, you can ask me. Okay, so we can discuss why it is not coming. Okay, so you should do the thorough derivation in your class note copy. Okay, that means in your fair copy that you need to be submit through online mode. Okay, to me. Then we can go for the small signal modeling. Okay, so the steady state calculation is over. Now we can go for that small signal modeling. Okay, so in case of small signal modeling, you know that basic method. Okay, so first you have to calculate that A1 A2, that you know that you have already calculated in previous calculation. Here you will get that value of A2 B2 C2 E2 and A1 B1. So now you have just replaced that values to that generalized equation. So it is your generalized equations for A matrices, for state transition matrices, and next one is your output matrices. Okay, so that you can replace them and you will find out that value. Okay, so small signal DC state equation you will get from here. Okay, again you are using that capping. Okay, capping means small AC variation values you have to consider. Okay, so here you can why that VD is considered as a 0. Basically you are making it fixed value, there is no value of VD. VD cap basically it's a diode forward voltage drop, so that is a fixed value. Okay, that's why you are making it 0. Okay, if you making it 0, so calculation will be quite simplified from your side. Okay, that calculation will be simple from your side. Okay, so I think you are able to understand that all the steps. Okay, so that I have already discussed, so that's why I am not again elaborately discussed it. Okay, I just show you the equations. Okay, for your benefit, so you can do it in your classwork copy. Okay, so then we can construct. Okay, so construct that equivalent modeling. Okay, so for inductor equations, so here you can see that here you can able to see that constructions of AC equivalent circuits. Okay, so in AC equivalent circuit, the small signal AC equations, okay, in scalar form. Okay, so that you are able to find out it. Okay, so here you are able to see that L di dt. Okay, L d I cap dt. Okay, L d I cap dt equals to d dash V cap t plus minus d r on into I cap t plus d V cap t plus Vg minus V minus IR on plus Vd whole into d cap t. Okay, so you will get that expression from that previous equation from here. Okay, so you will get that expression. If you evaluate them, so you will get this final one. So I kept it will be multiplied with this one. Okay, so row column multiplications and matrices. Okay, so here you are doing the same thing, and finally you will get that equations. Okay, that you will get it. Okay, so here you have also considered that Vg cap is there. Okay, so in previous calculations, first time calculation, so you are making that Vg cap is 0. Okay, for that simplicity for our calculation, but here you are considering that points. Okay, that is another additional thing. Okay, so you are to get that expressions from here, then another equations you will get over here. For that, it is for inductor voltage expression, it is capacitor current expressions, and finally IGT equal to DIT plus IDT. Okay, so that you are find out here. Okay, so Finally, we can go for that corresponding equivalent circuits. Okay, so in inductor equation you will get that equation, so that circuit is known to you. Okay, so that already discussed. Okay, then input equations. Okay, so it is also been discussed, and capacitor equation. So first inductor equations means inductor voltage equation, then input current equations. Okay, then capacitor current equations. Okay, so it is, that's why it is voltage source, it is current source. Okay, finally we will get that one. Then you can merge it. Okay, so after merge it, if you combine it or merge it, so you will get that individual circuit obtained, that is shown to us. Okay, so you can see that complete small signal AC equivalent circuit. So from that figure you can understand. Okay, so this portion is related to your input current portion, then inductor voltage portion, and finally you will get that capacitor current portions, that equation, that expression. This is KVL, KCL, and then the KCL. Okay, so in between that transformerized model is there, but it is AC transformerized model. Okay, that's why that is sign is in your AC. Okay, so if it is DC, then only one straight line will be there, but here you can see the isolation is there in between your current and in the input current and inductor voltage expression and inductor voltage expression to output your output current sorry, capacitor current expression. So all the cases you can see some alternating in nature you are observed over here, so that means there is some isolation in between of them. Okay, so you can, I think you are able to get it. Okay, then circuit averaging and the average switch modeling. So what are the importance of this one? Okay, so here you can see that circuit averaging and average switch modeling. Okay, so so what we can understand that circuit averaging was the first method. Okay, so I think one paper was there in 1975, that is written by Middlebrook. Okay, so first time that professor, okay, that professor Middlebrook and Chook. Okay, so I think all of you aware about the Chook converter, na? So Middlebrook and Chook. Okay, one of them are the PhD supervisor, another one is, both are maybe professors. Okay, but they are interlinked like that way. Means both are fellow professors, I think so. And first time they are derived that state phase modeling. Okay, that state phase equation. So first that is proposed by Middlebrook and that Chook. Okay, so some paper is there if you make a search in IEEE. Okay, so I just exactly, the date is not that year, maybe 1975 first paper, another one is 1983, maybe like that. Okay, I have to cross check it. Okay, so year may be different, but you can check it, so you can get that paper. Okay, that time in very old. Okay, so they are first time proposing this method, means small signal modeling method. Okay, these these two professors are that first inventor of this method. Okay, so that's why it is very after that it is famous method for modeling. Okay, so I told you now different modeling methods are available in literature, and right now also doing different those are doing the dynamical studies of that, any of the converter, means power electronics converters. Okay, so they are also using different type of modeling, they are not using directly that average modeling. But when that comparison, when that sophisticacy or that efficiency matters has come, okay, so efficiency matter has come, then they are comparing their modeling. Okay, their modeling of that converter with that average modeling. So that's the beauty of this averaging method, means it's a well accepted methods from any of the literatures. Then you can say like that in phasor diagram we are considering one reference parameter, am I right? So you can say like that averaging method, okay, also is an referencing parameters like that way. So how your modeling is accurate compared to your averaging method, so that is another study of another research work. Okay, so that's why in current scenario those are working on that modeling. Okay, so they are also giving their justifications based on that your standard means conventional small signal modeling or small signal averaging modeling means that will be decided by Medelov and Chu. Okay, that's why it is saying like that. Historically, the circuit averaging was the first method known for modeling the small signal AC behavior of continuous conduction mode PWM converters. Okay, you know that two modes of operation is available in switching converters. Okay, so one is continuous conduction mode, another one is discontinuous conduction mode. Okay, so both having some advantage as well as some disadvantage. Okay, so that's why sometimes we are also much more focused about some combinations of continuous and discontinuous conduction mode. That's why three state or tri-state converter concept has came. Okay, so as both of the features will be present there, means continuous conduction mode features as well as discontinuous conduction mode features, both of the features is present over here. Okay, so that's why both having that one. Okay, so in originally thought to be the difficult to apply some cases. Okay, so sometimes what happen, due to the complexity of that calculation, if you know that a lot of mathematics are there, those then mathematics is not so difficult to understand. It is simple mathematics. If you have the state equation, if you are able to write that switching equations, okay, then you can do that. You can use the different steps to find out that transformer, to find out that transfer function of the converter. Okay, or sometimes you are directly for different controller like sliding mode controller, you need not to go for that transfer function modeling or transfer function derivation of the transfer function for the plant of any of the switching converter. You can directly use the state equations or the state variables of the switching converters for that nonlinear control application like sliding mode control. Okay, so variable structure based control. Actually, sliding mode is the example of a variable structure based controller. Okay, so in that case you are using directly the switching convert, directly the state variables. Okay, there is no complexity. But if you go for that fundamental way or if you go for that conventional method, sometimes what happen if that converter having 8 modes of operations. Are you understand that 8 mode of operation? Definitely it is happen if you go for that fourth order boost converter or fifth order boost converter or buck boost converter, fourth order buck boost or fifth order buck boost. So in that case you can understand, you can see there is a lot of sets of equations. Okay, sometimes you can see 8 mode of operation means eight mode of operation means you can do realize that problem. So 8 mode of means you will get number of storing element means that is the order. Okay, that is the order of the equations. But 8 mode means you will get 8 times. Okay, you will get that 8 set of equations. Are you getting my point? So when you are going to be average them, so individual mode. Okay, so individual mode there will be different duties for D1, this D1 duty for mode 1, D2 duty for mode 2, D3 duty for mode 3, and D8 duty is for your mode 8. Okay, is for mode 8. So now you can consider that D1 plus D2 plus D3 dot 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 plus Dn equal to D. Okay, means all the duty cycle will be added, you will get the final duty cycle. So after that you are going for that averaging. Then what happened? It's a huge calculation. Are you getting my point? So it's a huge calculation. It's a huge set of equations. Then you should do lot of matrix multiplications. Okay, so again multiplication, then approximation, lot of that method will be too big. Okay, that's why sometimes you have to go for that some modified mode of averaging methods. Okay, so that's approximations you can consider sometimes. Okay, so that's the basic disadvantages of your normal of your conventional for your conventional switching converters modeling. Okay, so by using state phase averaging methods. Okay, that is written like that. So difficult apply to some cases. Okay, I think all of you will understand, able to understand what do you mean by the some cases. Okay, so there has been renewed interest and in circuit averaging and its corollary. Okay, so different corollaries are there. Okay, so you can use other methods that is based on your conventional switch mode, conventional state phase averaging methods. Okay, that can give you some modified calculations, means simplified calculation, not modified, simplified calculations. That method sometimes you can also follow. So one of the example of that method is average switch modeling. Okay, so average switch modeling, it is basically based on that AC/DC transformer, AC/DC transformerized based modeling method. Okay, like your previous one. Okay, can be applied. So it is your average average switch modeling can be applied in a wide variety of converters. Okay, so wide varieties of converter means higher order converters. Okay, some advanced topologies of the converter means that conventional topology, this is not for that conventional topologies, means you cannot get that modeling in any of the book. Okay, so you have only get that equations in the different research papers. Okay, so that's the important issue. So we'll use it in the model DCM. Okay, model DCM, and see it will be CCM, not CPM, so it will be CCM. Okay, printing mistake is there, and the resonating converters. Okay, also useful to incorporating the switching loss into the AC model CCM converters applicable for the three-phase PW inverter and the rectifiers. Okay, can be applied to phase control rectifiers. So if you see that different application, different position, you can see it will be applied for it different types of converter configurations. Okay, rather than that averaging and linearizing of that converter, the state equations. Okay, the averaging and linearization operations are performed directly the converter circuit. So you are applied it for the directly converter circuits. Okay, so you can see it. Here you can observe it. So port 1, port 2. So actually they are making it in the port wise application. So it is your time invariant network containing the converter reactive elements, means two energy storing elements. So that is your capacitor, another one is inductor. Okay, two energy storing elements are there. You can write the separate switch network from remainder of the converter. Okay, so power input is there and power output. So convention is your always the power input power and output power always be same. Okay, so that is your basic conventions. Okay, so that you should be keep in your mind. Okay, both of the cases that power configuration should be same. Okay, so here you can see that your energy storing element is capacitor. So which one is your state variable? So capacitor voltage is your state variable, and in case of inductor current is their state variable. Input side voltage is there. Okay, so that is Vg. Okay, another, it is your input voltage, so polarity of that one, so output voltage is there. Okay, so here you can see that load equation, so load is there. Okay, so now your is there, one forward control, another one is called feedback control. Okay, so here you can see two configuration is applicable for this model. So if you fetch the current from the output side, okay, output or inductor current directly, and that is controlled to the output side. Okay, so you are not taking any parameters from the input side. Okay, still it is there, input parameters are there, but you are not directly sense those parameters for your calculations. So you cannot say like that those are the these sorry, if you are not considered that input parameters directly to your calculation, so you can say like that is feedback control method. Okay, so if you consider that input parameters for your calculation, so you can say like that feed forward control. So I can take one example. Okay, so in normally normal conventions, that voltage mode control, current mode control, both of the control strategies that use are normally used for that feedback control in any of the control of the switching converters. Okay, where you in voltage mode control, what happen, you are sense the output voltage. Okay, that is your VT. Okay, output voltage of the converter, and you are comparing that voltage with your reference voltage. Okay, reference voltage means some of the reference voltage should be given to that converter. Okay, in your output side means op-amp. If you consider that operational amplifier, so some of the output voltage will be there. Okay, that may be fed, that may be put to the output. Okay, then you are comparing them. So after comparing, you will get some of the error signal. That error signal should be passing through a controller. Okay, any of the controller will be there as per the convention, means as per the requirement of the converter or as per the requirement of that application base. So arbitrary controller should not be there. You have to calculate, justify it. So why you are using that controller. Okay, so you will get some control circuit, control signal, then you can compare it some repeating signal. Okay, then you can feed that signal. PWM will be developed, that PWM will be fed to the driver circuit, and you can feed the output from the driver circuit to the switch of the converter, means switching converter. Okay, so that's a basic voltage mode control. But in case of current mode control, what happened, that you are sensing the output voltage. Okay, then comparing that output voltage with your reference voltage, so some of the error will be developed. That error will be coming back, error will be passing through that controller. Okay, so or the compensator. After passing through that controller to the compensator, okay, then you will get some control signal. Now you should compare the control signal, okay, with the inductor current. Okay, inductor current, are you getting my point? So you have to sense the inductor current. Okay, so if you sense it and you are comparing, the nature of the inductor current is look like your repeating sequence in voltage mode control. In voltage mode control, you are not sensing the inductor current. You are using some sawtooth waveform. Okay, you are that sawtooth or triangular waveform is coming from your function generator, and that is deciding the switching frequency of the converters. Okay, switching frequency of the converter. But in this case, in current mode control, you are directly sensing the inductor current. So what is the nature of the inductor current? It's the nature is look like a triangular wave. Basically, when inductor is charged, or inductor current will be rise up or ramp up with some slope. When inductor is discharged, it will be ramped down with having some slope. So it's look like a triangular one. Okay, it's look like a triangular signal. Okay, now you can compare that inductor current with your control signal. Okay, after comparing, so again you will get some of the values. Okay, so definitely there is some controller. Okay, after the controller, again it will be actually reference current will be developed. Okay, so I have just forgotten one thing. Okay, so some reference current you need to be give over there. Okay, so from the reference current is coming from your inductor current. Okay, another is your control signal directly coming from your voltage. Comparing them. Okay, after sometimes you are also using some controller. The time, the rise time, not rise time, the you can say like the time constant. Okay, the time constant of the controller. Okay, in current mode control. Okay, that means the time constant of the controller in current loop should be very high. Okay, should be high, comparatively minimum 5 times. Okay, time response is comparatively 5 times compared to your controller in your voltage loop. Okay, I think you are not able to visualize the rest, all the whole thing. So some of the I will discuss in my next module. Okay, when that control will be coming. Okay, so I'll having some separate module. Okay, so control designing of that switching converter, at that module I am going to be discussing. Okay, so voltage loop control, current loop control. Okay, in current loop control both of the loop will be there, voltage loop and current loop. Only in voltage loop control only voltage loop is there. So why the transfer time, sorry why the time why the time constant is different in current loop and voltage loop, that also we discussed. Okay, in current loop that controller having better time constant, okay, compared to your voltage loop controller. Okay, so that's why the response also be very fast, okay, in current loop. So it is example of a feedback control. Okay, so it is also applicable for buck converter, boost converter, buck boost converter. Okay, now what is feed forward control? If you know about that, PFC means power factor corrected controller. So why it is called power factor corrected, sorry, PFC converter, power factor corrected converter? Why it is important? Sometimes what happen, power factor means you can understand that input, so in that case, in power factor control, okay, power factor corrected converter, so corrected converter, okay, means if you see, only you are calculating that in the output side, okay, so there is no effect from the input side directly. Okay, indirectly definitely there is some effect. So input parameter is changed. If input parameter has changed, so there is an effect to the output parameter. Okay, output of the converter. Okay, so that it's an effect. But what happens sometimes? Sometimes what happens? So direct effect is required, like your PFC converter. So what happened? We are also fetching. We are also calculating the input current. We are also tracing or sensing the input current. Okay, and that current is processing. Okay, so output signal also being sensed. Okay, output signals are also being sensed, and the input current, okay, also being sensed. Okay, so that is called feed forward control for the processing of that PWM. Okay, processing of the PWM means end of the day you are comparing, you are developing one control signal. Okay, so end of the day you are developing or generating one control signal. Okay, and that control signal is compared with your repeating sequence. Okay, and you are getting that PWM. Okay, that PWM is feed to the converter switch through driver circuit. Okay, so in case of feed forward control, what happened? So that generations of that control signal, there is some direct effect. Okay, there is some direct effect of your input side current. Okay, sometimes we are also considering input side voltage. Okay, so I am giving another example so you can understand well. Okay, so that is example of a PFC converter is an example of a feed forward control. Okay, feedback as well as feed forward control. Okay, so it is on conventions. Okay, next one, if you, I think all of you heard about the term maximum power point tracking. Okay, so MPPT controller. Okay, so right now lot of works is most of the works is switched to the renewable energy based works. Okay, we are also working in this domain. So when we are means basically MPPT controller is used, that means extracting, okay, extracting maximum power. Okay, extracting maximum power from your solar panels. Okay, so MPPT is not using only for the solar panels, it is also using for wind turbines. Then pico hydel also you can be used. Okay, so it means DG set, hydel or DG set, you can say like that way. Basically you have to extract the maximum power point, means all the conditions, if the environment condition has changed. Okay, basically renewables are the example of intermittent. Okay, intermittent in nature, means always time variant, their parameters, their output is always time variant. Sometimes it is high, sometimes it is low. So you have to, I am telling you now that power input should be constant from output and input side. Okay, so that's why you are much more focused about maximum power extraction. That's the basic motivation. So constant voltage, constant current, they are not working on it, they are always working on it, all the condition they should take the maximum power. Okay, so voltage may be different, current may be different. Okay, if voltage is high, so current will be low. If current is high, voltage will be low, but power will be constant throughout the path. So in any conditions, any solar, any types of solar irradiation, solar temperature, means environment temperature has changes, but all the time you should get that maximum power point. So that's the basic motivation. So in case of MPP, means maximum power point tracking converter, so there also you are using some switching converters. Okay, means integrating, means what is the purpose of the switching converter? So it is providing you that voltage. Okay, it is providing you that output of that converter is always voltage. Okay, that voltage is fed to the DC bus. Okay, so DC bus means DC link voltage source will be there, that will always taking the power from your renewable sources, means solar panel. Okay, and it will be feedback to your, sorry, it is extracting power from the solar panel and giving to that DC link voltage or the bus voltage. Okay, DC bus. Okay, so in this case your output is not more concerned, you are not concerned about your output, but you are only concerned about your input parameters. Input parameters means what? In solar panel, when you are extracting the power, so which power is the multiplication of what? Current and voltage. Okay, so you are much more focused about how much voltage is developed or how much voltage is generated to the solar panel. Okay, how much current is there. Also in solar panel you can also do testing like your open circuit testing, like your no load test, you can say like that, how much maximum voltage may be developed by the panel. Okay, with maximum irradiations, okay, or the temperature, like that way, and how much maximum current will be developed over here if there is circuited path is there, means you are shorting the solar panel output. Okay, then you are calculating the how much maximum current is there. Okay, so it totally depends upon the rating of the panel. Okay, so voltage and current, both two things are, two parameters are important. Okay, so you are extracting that one, so you are not bothered about that output voltage. Okay, so you are extracting only the maximum power point you should be maintained. Okay, so it is your consideration, prerequisite of that one. So totally your that controller is there. Okay, there is some boost converter. Okay, so the input of that boost converter directly connected to the solar panel. Okay, that voltage current is coming from the solar panel, then boost converter is there. In output side, that boost converter, you can say like that, output is connected to a capacitor through the DC bus, you can say like that. Okay, so the boost converter is there, the switching pulse of the, how would you control the switching pulse of the boost converter? So definitely if you go for the maximum power point, so you have to analyze this. Okay, you have to calculate that voltage and current for the every instant. So which type of voltage? Input voltage and input current. Okay, so you are not sensing the output voltage, so you can say like that, it is example of a feed forward control. Okay, and the switching pulse of that boost converter is controlled with that feed forward parameters, means input side parameters. So that's why it is known as feed forward control. So I think you are able to understand why they are that switching network is shows like a two port one. Okay, port 1 and port 2. So in port 2, if you consider, so you are considering output side parameters like output current, output voltage. Okay, so and control input is always be there. Control input means how to get that value in dt. Okay, and input side two parameters also be there, I1 and V1t. Okay, so it is plus minus is there, so network is look like a two port network like. Okay, so there is no input parameter, so you are not considered this one, directly control output will be there. Okay, means control output is coming from your where, coming from your that means differential amplifier is there, that output is sensed like that way. So that's why it is called the control parameter. So when you are model that converter in practically, so I think this portion, up to this portion, you are able to understand that why they are two port structure they are considering and they are showing here. Okay, I think there is no problem about it. So now I am telling you another important points. Okay, so when you are going to model that parameters, okay, when you are going to model that converter, okay, so at that time you have to much more focused about at the time you have to give much more focused about which how would you represent, okay, how would you represent that converter. Okay, so if you can do it in you can test it in MATLAB. Okay, so in MATLAB, how would you simulate or compute the entire switching parameters. Okay, you can do it in testing for your home assignments. Okay, no problem. So normally what happened, first one method you can do it, that calculations. Okay, so all the calculations you can use that m file means where you can write the program, or where you are able to write that coding of that converters. Okay, coding of that converters means you can say like that what is their input parameters are there, so input voltage, input current, input output current. Okay, so inductor value, capacitor value, then you can use some switching combinations always be there, so you can write some code. Okay, means switching logic. Okay, logic normally written in the code form. Okay, so what is your switching logic, and you can calculate it through that path and you can process it, and finally you get the output means what is your step output means step response. Okay, or the Bode plot, like that. It means time domain output, frequency domain output. And sometimes if you calculate the controller, so you can do it in M file, no problem. So all the differential equation should be written in the M file. Okay, that is process number one. In second process, what you can do, you can using that standard mathematical calculations. Okay, all the calculation you can do it in the M file. Okay, after completing all those calculations, okay, then you have some generalized structure of some generalized transfer function. Okay, you have it with you. Okay, so if you have that one, so you can get the transfer function after calculating all those values. Okay, in M file, so you have some final transfer function of your converter plan. Okay, so you can now you can use some model MDL file. Okay, so one is M file coding. If you write a code, okay, for MATLAB, so you have to use some script. Okay, that is M file. The extension of this file is M file. If you go for that modeling based converter modeling, okay, means drag and drop. Okay, you can directly use from Simulink module. In MATLAB lot of modules are there. Okay, so Simulink is an example of one module. Okay, like a control system block is there, means different toolbox are there, different module. MATLAB is a combinations of different toolbox and module. If you want to purchase the MATLAB, so you have to give requisitions to MATLAB. Okay, so which toolbox you want to purchase. Most of the time what happen, in institute, okay, institute procuring some license. Okay, institute is procuring from license from MATLAB. Okay, so for they're taking the license for different toolbox. Okay, not for all the toolbox, so mostly used toolbox normally institute is procuring from the MATLAB. Okay, so number of users. Okay, so different. So in that case we are using that Simulink module also been on toolbox, like that. It is mathematical toolbox means all the mathematical tools are there. Okay, so in Simulink module, if you use, so directly you can drag some of the point. So transfer function block also be there, generalized transfer function block. Now you can give the denominator values matrix form in denominator and numerator, so that you can get from your M file script. Okay, so you can represent your switching converter in the form of transfer function. That is, you can say like that. It is LTI system. Okay, then you give some input to that switching converter. Means input means which type of input, not the power input. Okay, so power input is already there. When you are calculating the transfer function of the switching converter, it's a function. The transfer function is a function of your input voltage, okay, output resistance, inductor value, capacitor value, load resistance, ESR values already there. So if you want to give the input to that transfer function, so that input will be a reference input. Okay, means reference input means that how much output voltage you want to get. Okay, that reference input will be there, and you are getting that value. You will get the output voltage. That voltage will be sensed from your output side, and it will be compared with the controller circuit. Okay, in case of controller, transfer function you are using. Okay, not that controller circuit. Okay, so it should be in transfer function form. Okay, then you feed it to the comparing with that value, and you will feed it to the again that converter input. Okay, I think you are able to understand. That is your input, converter input. Okay, so it is one method. Another method, it is second method. Then third method, you can write all the differential equations of the switching converter in MDL file, means in your model form. Okay, so integration will be there. Okay, so normally you are using integration. So basically IL you want to calculate from DIL dt. So definitely you have to integrate that parameter. So integration you have to use, you can calculate them. So in last method, if you go for that integration, so all the value you can fetch over there. So you are not directly going to approximate that value. So we are calculating the state variables. Okay, and that state variable you can implement any of the calculations. That is another well-known method. Okay, in that case we have to give some duty cycle. So average equation you have to write down. Okay, but average differential equation you have to write down. Then you can simulate or compute it through the MATLAB. Okay, so in this case you no need to write that in script file, means end file. Okay, you no need to write any code. Okay, you have to derive that you have to derive the transfer function of that controller, and rest of the thing you can using the differential equations. Okay, in case of controller you can also using the differential equation, no problem. So what is the benefit of that last method? That benefit is you are fetching, you are considering all the non-linearities without making it averaging. So that is your separate switching network from switched modeling. Okay, that is called switch modeling. Okay, so I think all of you are able to understand that what I am going to discuss over here. Okay, next you can see that boost converter model in switch method. Okay, so here your boost converter model. Okay, it is your ideal condition. So your input voltage is there. Okay, input current, your inductor current is there. So inductor is connected over here. So switches are there, then diode. Okay, then capacitor, resistance, all are there. So there is no non-linearity. So what is the consideration here? So ideal boost converter is there. So you are making it. Here you can see for switch on condition, for switch off condition. This is for switch on conditions, and this figure is for switch on condition, and second figure is for switch off condition. In switch off condition you can see over there that two port wise you are considering. Okay, so I1 V1 you are considering. From this one your I1 is what? I1 is your IT, and what is your V1? V1 is your VG. And in second case same thing also be there, but first case the diode is conducting. Okay, first case the diode is conducting, so you are getting the I2 from here. In second case, that direct, there is no direct interaction of the diode, means diode is there but it is not directly conducting with that MOSFET and diode. Okay, so that portion will be open. Okay, in second case, means when switch on, so it will be what? It will be there will be no current flowing through this diode, but you can say like that some of the current in I2 you can consider that I2 will be similar to that current then we actually no current will be there. Okay, but in second case that definitely the I2 will be there. Okay, but that two modes of operation, two port configurations are there, so you have to calculate the value of I1, I2, V1, V2. Okay, so two ways of defined in switching network. Okay, for switch on condition, switch off condition. What we can discuss from these configurations. Okay, so the number of ports. Okay, the number of ports in the switch network is less than or equal to the number of SPST, means single pole single throw switches. Definitely the number of mode of operation. So if the switch having two modes of operation, means switch on operation and switch off operation, switch on and switch off operation, so definitely the total setup number of port will be what? 2. Okay, for switch on condition one port network will be there, two port network will be there. Switch off condition another two port network will be there. Okay, that is the motivations. Okay, that is suggesting by that calculation. So simple DC-DC case. Okay, simple DC-DC converter, INU is the converter contain two SPST switches. Okay, when switch network contain two ports. Okay, means that I am told you, but it is not same for all the cases. Okay, sometimes what happen, so some complicated converter topologies are there. In that case definitely there will not be the two set of equations. Okay, it will be more than different set of equations. Okay, that's the thing. Then in switching terminal, then the switch network terminal waveforms are, then the port voltage and current, currents will be there. Okay, that is V1T, I1T, V2T and I2T. Okay, so to put so configurations there. Okay, so next one you can say like that. Next one you can say like that, two of these waveform can be taken as independent input to the switch network. The remaining two waveforms are then viewed as dependent output of the switch network. Okay, so it depends. So which one will be independent sources, which one will be dependent sources, that will be directly coming from the calculation. There will be no complexities, okay, that you are already doing in previous sections. Okay, so that KVL KCL you will getting some of the values and you can implement it. Definition of the switch network terminals quantities are not unique. Okay, different definition lead equivalent results having different forms. Okay, so you have to focus about the equivalent circuits and equivalent forms. Okay, next, boost converter example you can see for definition so on. So since I1 I2 contains the converter inductor currents, okay, the output voltage, it is convenient to define these waveforms an independent input to the switch network. Okay, that switch network dependent output are then that V1 and I2T. So here you can see that mode 1 condition, that's why it is written A. So it is your boost converter, basic circuit of the boost converter, ideal boost converter. Okay, it is non-ideal, it is ideal boost converter. So that's why they are not considering ESR in L and ESR in C. Okay, so that I1 V1 you have to have that value and you have to calculate I2 and V2. Okay, that mathematical steps you can use over here. Then obtaining the time invariant. Okay, so time invariant network modeling and terminal behavior of the switch network. Okay, so you can see that the configurations is already there, like you if you, in analog electronics. Okay, in analog electronic circuit, okay, you are doing the same calculations for each parameter. Okay, calculations of the each parameter. So so you can say like that your input is VG. Okay, so in VG input is coming, so plus minus voltage is there, so inductor is there. Okay, so IT and I1T is there, and that I1T and VT will be directly coming from that points. Okay, so it is your current source, voltage source. So the directly I2. Okay, so V1 you can say like that, V1 means it will be the voltage source, and I2 definitely it will be the current source. Okay, so that V1 is dependent on what, that I1 and VG. Okay, that's why it's a dependent source. And in I2 definitely it will be dependent on your what, V2 and your input side and your left hand side means input side parameters. That's why that current also independent one. Okay, so now you have to calculate it. So from where directly I am getting this circuit, that you can see the two-pole network in circuit theory. I think you remember this circuit theory. So directly that circuit configuration, why we are putting this manner. So directly coming to the circuit configuration. So one independent source, it is like H parameters calculations. Okay, means H parameters of the transmission parameter calculation. Directly you are coming from that one. Okay, so then definitions of the dependent generator waveforms. Okay, so different waveforms are there. Okay, so V1 configuration, when V1 you have to calculate. So first up to 0 to DTS it is 0. Okay, then it is coming V2. Okay, so if you making it average, so it is coming V1T average with the cycle of TS, average with the time period. Okay, time period of TS. Then you can calculate the value of IT. Okay, IT is your average with your time period TS. Then I1. Okay, then you are making it you are making that circuit configurations, average circuit configuration for switch network. Okay, now waveform of the dependent generator be the identical to the actual terminal waveform of the switch network. Okay, the circuit is therefore electrical identical to the original converter. So far no approximations have been made. So here you are not going to discuss about the approximating method. Okay, so the Okay, so far there will be no need for approximation, so you can directly use that set of equations. Okay, so for that calculation purpose, now different circuit averaging steps. Okay, so in steps you can use those formulas directly for getting the waveform. So in that case, you are considering previously you are using that state equations or state variables, that C and L. Okay, now you are using inductor current and sorry, average inductor current and average capacitor voltage. Okay, so all the parameters are average, so you have to calculate all the averaged values. Okay, for that averaging value, you know that you can use that standard method. Okay, so by using standard method you are able to calculate all the average values. Okay, so then you can replace them, and you can see your output voltage, you are also using that average value. In input you are also using the same average value, that power input, loads, all are there, and in output side you are using that resistance. Okay, resistive load you are using. If you change that load again, that all the thing will be different, but normal convention, normal calculation, we are considering only the resistive load. Okay, so average switching network. Okay, so how to make it average? So you know that method, so you have to integrate that up to t to t plus ts, and over the period you have to make it average. Okay, so in control input you have to calculate that value of dt. Then what is your calculations, what we can conclude from this study? Okay, the basic the basic assumptions in made, that the natural time constant, okay, natural time constant of the converter are much longer than the switching period, so that the converter contains low pass filtering of the switching harmonics. Okay, so what is the purpose of low pass filter? So you know that mitigating or minimizing the effect of switching harmonics, you know that one. So if you do the FFT calculation, so you can see that fundamental one, and as well as that multiplications of your fundamental switching harmonics, that you can calculate it. Okay, after getting that calculations, so you can omit, you can reduce that harmonics by using low pass filter. Okay, one may average the waveform over the internal, one may average the waveform over the interval that is short compared to the system in natural time constant. That I am telling you now, time constants play the important roles for the dynamics of the switching converters. Okay, so if the time constant is more, so automatically it will try to settle down the steady state value. So there is some huge or drastic effect on the dynamics of the converter. So how do you realize the drastic? So if you increase the p value, means proportional value of a controller, then what happen? If that converter parameters are fixed, okay, that is fixed for throughout the calculation, so you are making it fixed, there is no problem. But if you increase that proportional value, so then what happen? That overshooting, that converter dynamics or converter response will be high. If that overshooting is high, if you consider that path of trajectory, okay, trajectory means one, in my last class I told about, in phase plane what happened, one state variable is your x-axis, another state variable is in your y-axis. Okay, so x variable means that current or voltage, inductor current or capacitor voltage. If that controller parameter means p value is high, means kp value is high, then that trajectory will be different. Okay, if the trajectory will be different, means the boundary. Okay, so eigenvalues, so converter having all the roots, okay, means it having some of the eigenvalues. Okay, for on time condition and off time condition, that switching of that eigenvalue or jumping of the eigenvalue from on time to off time. Okay, if the trajectory is definitely there is some boundary region. Okay, so in between the trajectory should be there. Okay, means suddenly if your overshoot, peak over percentage of peak overshoot is very high, then what will be the problem? Percentage of overshoot is very high, that may cause for instability. Okay, that may cause for directly converter may enter to the unstable conditions. Okay, that overshoot is too high. So you can consider that in your calculation, when you did your calculation, you can say like that your percentage overshoot, your maximum tolerable percentage of overshoot is 20%. Okay, suddenly what happened to try to make in steady state value, so suddenly you are increasing the gain, that means proportional gain at range, that percentage of overshoot is coming beyond 50%. Okay, so what will be the problem? So suddenly what happened, that converter will be made comes to the unstable condition, or you can say like that there is observation of some instabilities. Okay, so because of what, that the trajectory boundary. Okay, so that means on state to off state, so all the roots of the converter is jumping from on state condition to off state conditions. Okay, if it is jumping from on state condition to off state conditions, so what happened, there is some boundary of that trajectory boundary. So if that trajectory path is beyond of your considered boundary, then what happened, so converter will directly goes to the unstable conditions. That's why time constant is more important. Okay, time constant have important points or important considerations for the prerequisite for converter controller designing. Okay, so if the time constant is very more than of your design value, so response will be very fast. Okay, so that response will be die out very fastly, but the problem is that stability issues, that you will not good stability. Okay, so you have to design the converter and the controller so such a manner, switching converter and the respective controller of that converter such a manner that trajectory or the time constant are having that moderately value. Okay, otherwise converter will be unstable. Okay, so that is written that system natural time constant, that short compared to the system natural time constant without significantly altering the system response, that I am telling you. So normally we are considering underdamped system. Okay, underdamped system means it is moderately underdamped tends to critically damped. So you have to design the system look like a critically damped, but consideration will be underdamped system. That's why overshoot is there, na percentage of overshoot is there. Definitely for it will be that underdamped system. Okay, so you have to reduce the percentage of overshoot. You are trying to die out the percentage of overshoot, but the problem is that rise time will be less. If the rise time of the system is less, means system will be slow. If rise time is system will fast, rise time will be less means system will fast. Okay, if rise time will be more, okay, time constant is more means rise time will be more, so system will be slow. So definitely the rise time in underdamped system is less compared to your critically damped system. So your convention will be like that, your all the parameters rise time will be less, as well as your overshoot will be died out, means die out, means overshoot also be less, rise time also be less. Practically they are inversely proportional. If rise time is less, overshoot will be high, means response is very fast. Okay, if overshoot is less, rise time will be more. So both are practically inversely proportional, but you have to make it in a such a manner so moderately rise time will be moderately less and overshoot will be moderately less. Both should be like that. So you have to select that manner. Then in particular, the averaging over the switching period, that is TS, remove the switching harmonics. Okay, so if you using some good filter, okay, so you can omit that one while preserving the low frequency components of the waveforms. Okay, in practice, the only work need for this step is to average the switching dependent waveforms. Okay, so we have to design that waveform in such a manner. So switching waveforms. Okay, that means average. How do you will look like that waveform of your state variables? Means voltage, current. How it will be look like after averaging? That is important. Averaging the boost converter example that I am telling you, so you can combine them. So okay, so it is your switched network is there. Okay, so averaging for the boost converter, so it is your VG. Okay, so that portions are already there. We discuss the voltage source, current source, dependent voltage source, current source. Now you are making that currents are the averaged. Okay, so you are making it average IT TS, that VG TS. Okay, so all the parameters are average, you can see over there. Here it is only the actual one, then you are making it average. Okay, so then you are calculating the most of the things. So average switch network, it is switch network. Now you are going to make it average switch network. Okay, After compute the average values for the dependent source, so you are getting like that V1t average over the time period Ts. So it is coming d dash t within bracket V2t Ts. So why it is like that way? So definitely that V1t is it coming to what? V2 Ts. Okay, but there is some 1 is to d or 1 is to d dash like that phenomena was there. Okay, that's why you are written like that, that V1t. Okay, so what is your V1? So V1 is like that, this portion your V1. Okay, so V1 TTS it is coming d dash V2 TS. Okay, so V1 by V1 TTS whole divided by V2 TTS, it is coming d dash. D dash means 1 minus d. Okay, so 1 minus d means 1 by 1 minus d equal to V2 t ts by V1 TTS. You are getting it from that boost converter modeling. Okay, so you know that expressions. Okay, directly you are getting from that boost converter. Okay, that duty weighted formulas. Okay, so directly if it is average, so definitely you are making it like that. Similarly in current it will be reversing. So voltage means what? In transformer what happened? The current and voltage, that means V1 by V2 equal to N1 by N2 equal to I2 by I1. Okay, in transformer. Same thing also happened here. Okay, V1 T within bracket Ts equal to D dash T within average V2 T Ts equal to I2 T Ts with D dash T is I1 T Ts. Okay, you are getting that formula. So it is your V1 expressions. Okay, average value of V1, it is V2. Then same thing also happened for I2, it is average value of I2 and I1t. So you'll get that expression. Now you can replace that value. Okay, from here we are replacing that value from here. Okay, so we are replacing that value. These two values are going to be replaced in form of voltage. That's why this is dependent. Okay, so in form of V2, it depends, that voltage is depends upon your V2 voltage. Okay, that V2 voltage, average V2 voltage. Okay, and that current is depends upon your I1 current. That means I2 current, I2 average current is depends upon your I1 current. That's why both of the voltage and current is dependent in nature. Okay, so it is an average switch model, so you can calculate that values. Okay, so details calculation I am not given. Okay, so that is similar thing, na? That's why I am not mentioned, but you have to calculate in your homework copy, means classwork copy, that recheck all the steps. Okay, it is coming or not. Then perturbations and linearize, you can do it, perturbations. Okay, then average value will be like that, your DC steady state value plus capping value and small AC variation. So duty, this is your input voltage. Okay, then it is for duty. Then on time duty, okay, dt, and it is your off time duty. Okay, so off time duty 1 minus dt, it will be d dash. So 1 minus d minus plus minus d cap t. So it will be like the 1 minus d means d dash minus dt. Okay, so that's why d dash t, it is d dash minus 1 minus dt. Okay, in input current you are getting like that, steady state current plus cap current, voltage, output voltage, then steady state output voltage waveform like that way, V2 and steady state value. Then V1 will be look like that, V1 steady state value plus AC variation value. I2 the same thing also be there, TS plus I2 plus I2 cap is there. Okay, so circuit becomes look like that. Now you are making it constant value plus time varying value. Okay, so again the same thing, constant plus time varying value. So you can multiply those values. So replacing, so previously you are replacing and again you have to multiply it. So if you multiply it, again some multiplication of two capping value means non-linearity, you can omit them. So same thing you can follow over there. Okay, so depends dependent voltage source value. So how it will look like? So you can multiply them. So this value is your non-linear second order. So again you are making it neglected. So finally you will get that multiplication v dt, v d cap t, minus plus is there, again plus minus d dash v plus v cap t. Okay, that portion you are getting. Then dependent current source. Okay, same thing, again you are going to be multiply them. So if you are multiplying them, so again you are getting that equations. So I cap t dt, that non-linear portion you can omit. Okay, if you are able to omit it, so then you will get that value d dash I plus it cap T into I into D cap T. Okay, so that current source value is there. Okay, that is dependent current source and it is independent current source. Then linearizing circuit average model. So now you are replacing. So it was your final one. Okay, so final one value is there. So now you are replacing all those value. Okay, all those value. So additional voltage source is coming. Okay, due to that linearizing that value dependent voltage source. Okay, in this case additional current source also be coming. Okay, with your dependent current source, it is independent current, so it is independent voltage and it is your dependent voltage. It was there already. Okay, if that current source is new compared to coming to that calculations, then you are making it averaged. Okay, so here you can see that both of the cases it is not isolated, it is connected. Okay, that's why that connection is coming. Okay, that short circuiting portion is there due to basically you are using the same neutral, no? You are using the same reference parameter. Okay, that's why that negative all the cases are same. So datum node is similar for all the calculations, that's why you are making it. So one portion is your AC, another portion is your DC. Okay, so sinusoidal is for AC, another straight line is for DC. That's why AC DC modeling. Okay, AC DC transformer modeling, like that. It is D dash one. Basically, it is D dash is there. That's why it is D dash one is there. Okay, so I think you are able to understand that calculations. So what is the summary that switched averaging method? Okay, so from the summary we can understand. That circuit average. Okay, that circuit averaging method, the model of that switch network. Okay, that model of the switch network with the equivalent voltage and current sources, such that an equivalent time variant network is obtained. Okay, equivalent time invariant network means time is not changing. The average converter waveform over one switching period to remove the switching harmonic. Okay, so it's remove the switching harmonic, perturb and linearize the resulting. So you are perturbing and linearizing the resulting two frequency model and obtain the small signal equivalent circuit. Okay, so that is your motivation. So finally your motivation is calculate the small signal equivalent circuit. So till now we are using different method of switching converter modeling. Okay, so I think all of you are able to understand. If you have any confusion, you can ask me any questions, so we can rediscuss some of the portions. Okay, definitely that portion, confusion portion, again we can rediscuss. So normally I am all the time following that portions is Ericsson book. Okay, fundamental of power electronics Ericsson book, you can follow that books. Okay, so no problem. So if you facing any kinds of difficulty, you can ask me. Okay, so today I am covered up to switched averaging model. In my next class, I'll discuss about the canonical circuit model. Okay, so another few slides was there. Okay, that will be covered in my next class. Okay, so if you have any kinds of doubts, any kind of confusion, you can ask me. Okay, so I can discuss some of the points. But my suggestions, all the students, that you should up to date. Okay, that today I am covered that portion, you have to up to date to your home. Okay, and prepare your fair copies. Okay, after completing this, that is my third module, I think so, third or fourth module, I think. I just need to recheck it. So after completing my this module, I will give you a few days, 2-3 days. So after that you have to submit your class note, so online. Okay, that your CR will send you the link and he collect that one, he will collect that all the documents. So day to day you have to update yourself and you can follow that books. Okay, any other books you can also follow, like Ned Mohan book, Philip T. Klein book, other books also be there, N book is there. Okay, so the but basic you have to take one reference. So reference you should pick that Ericsson book. Okay, that book you should pick as a take as a reference, that I am following. Na? So different methods I have discussed. Okay, so I hope you don't have any doubt right now. So if you have doubt, you can ask me. So Okay, so if you have any doubt, you can ask me. So no problem. So okay, so right now I am ending my session. Okay.